Welcome to Lecture 17. What we want to do today is we want to pick up, sort of go back to mixture proportioning. As we left the last few classes, we were talking a lot about admixtures. What I want to do today is I want to jump into mixture design again, and I want to start to talk a little bit. I'll do a very practical example, and then we'll jump into what we can do with the admixtures from there. We can see a picture here of while you may not have had the best week in the world, or you may think your job's not so great, I will promise you that there are some other jobs out there that may not be better. I have no idea why anyone would have a picture of this, but I found it on the internet and felt the need to share it with you because it brightened my day, and I think this is the type of afternoon where it may brighten your day too. What we want to do, though, is talk a little bit about mixture proportioning. We want to give you some practical information on mixture design, and then give you some questions that will help you be able to answer some of the problems much more quickly. I'm going to go fairly quickly through an example out of PCA Design and Control, just sort of to run through the numbers to get us back up to speed, and then we'll talk a little bit about some of the adjustments that we can do for these particular mixtures. This example, you'd be asked to design a concrete mixture for a foundation element. The specified compressive strength is 3,500 psi. You've got 3 inches of cover over top of the reinforcing steel, 4 inches of distance between the reinforcing bars. The only admixture that's going to be used is air, and there's no statistical information that is based on any of the previous mixtures that have been out there. One thing I will mention, there are two things I'll mention as sort of part of class business. One of them is there was a question on the costs of different admixtures. I have a call in. I've been told my answer is waiting as soon as I call back in to get my answer. So on Monday, we will be able to give you some information on the costs of the different admixtures. The other question that I've gotten at least twice now, there's a question on fineness modulus, and there is an error in the notes. If you try to calculate fineness modulus the way that I calculated it, and you try to get the same numbers, if you get the same numbers, I'll be impressed, because I spent 15 or 20 minutes this morning trying to get the same numbers that are on the slides, and I have no idea how to get those numbers. But I have posted an example with correct numbers. It's in a Excel spreadsheet, so you could actually use that, and it's up on the website so that you can download that and use it. So to go through this example, example 1, again, we've got our 10 steps from ACI. We'll begin by providing the information on our available materials. We've got an ordinary type 1 Portland cement, 3/4 inch maximum size aggregate with a specific gravity of 2.68, 0.5% moisture content on an SSD aggregate. Dry rotted bulk weight is 100 pounds per cubic foot. Moisture content is 2%. Fine aggregate to natural sand with specific gravity of 2.64, 0.7% absorption, moisture content of 6%, and a fineness modulus of 2.8. The second step in the process would be to choose a slump. As mentioned, this is a footing, this is a foundation wall, so it would be in this, the second row, and between the two columns we could see that we would be targeting a slump of somewhere between 3 and 5 inches. I will simply select the 3-inch, although this obviously is going to depend on what? What are some of the things you need to consider before you select a slump?
Water to cement ratio? No, that was wrong.
Not water to cement ratio? Where you're going to be replacing it, who's going to be replacing it, what equipment they have to be placing it, how easy it's going to be, what's the level of congestion that you expect with the reinforcing bars. There are concretes that are placed with a 0 or even what's referred to as a negative slump type mixture. Those are typically placed with heavy vibration and things like a slip form paver. There are other materials that have a very, very high slump because they're going to be placed in a region that's very, very difficult to get to. So you want to try to choose a slump that's appropriate for the equipment that you have available. For this case, I would assume that we would have something that would enable us to do a reasonable job placing the concrete. Step 3 is the aggregate selection. As mentioned, we're using a 0.75 maximum size aggregate. This is typically going to be dictated by the aggregate that's most commonly used at a particular place that you're working. Unless you're doing a lot of material design and you're going to start buying different types of aggregates. In that case, you may actually go out and try to find the largest aggregates that you can. The few things that you need to check. You need to check that it's less than 3/4 of the cover, which it is. It's less than 3/4 of the distance between the reinforcing bar, and that it's less than B/5, which is the distance in the formwork. If it was a slab on grade, remember the requirement is D/3. Step 4 would be estimating the mixing water and air content. So we've got a 3/4 inch aggregate, so it would be somewhere in the 3/4 inch column. We have a 3-inch slump, so we would be in that row. And this would lead us to something like 305 pounds per cubic yard. And I will actually cross this out and make this pounds per cubic yard so that we've got the right units. I apologize that the units in this particular table aren't right. So we would pick 305 for this particular example, and depending upon the exposure condition that we would be somewhere down in this range right down here, from a mild exposure to a severe exposure. Now, one of the things that I will point out at this point is I will point out that we may be able to make an adjustment right at this point depending upon either the fineness of the cement or the gradation of the aggregates. And I'm going to assume that the gradation and the fact that the aggregates are relatively smooth will enable us to reduce the water by about 30 or 35%, about 10% reduction. So I'm going to, even though the chart says 305, I'm going to take that down to 270 based on local history of the aggregates and move forward from there. In addition, I am going to use 6% air, and this may not necessarily be only based on the exposure conditions. We said that there were other reasons why you might want to use a higher air content. And anybody remember what those might have been? You can lose air, and if you are going to make an error, if you are going to air with air, you want to air high. Okay, if you're going to make an error, you're going to miss the target. You want to be missing the target slightly high rather than slightly low. The other thing that I will point out is typically, and this is an economics issue, typically the cost of putting in a little bit of additional air more than compensates for the amount of cement that you're going to be pulling out of the system. Air will also help in your workability. It will also help in making the concrete a little bit more cohesive and a little bit easier to place. So many times you'll be seeing an air entrainer used even if it's not needed for freeze-thaw resistance, just because it makes the concrete a little more economic and a little bit more workable, the overall system. Selecting the water to cement ratio. For our particular case, we don't have to worry about de-icers or aggressive substances. If we had to worry about de-icers or aggressive substances, we would be making sure that we stayed below one of these other water to cement ratios. Again, remember corrosion, especially when it's exposed to chlorides, we'd stay below a water to cement ratio of 0.4. Freezing and thawing with de-icers, 0.45. And then low permeability, we'd be looking at a water to cement ratio of 0.5. For our particular example, we don't have any of these limitations, so we are going to base the water to cement solely on the needs of strength-based design for this particular problem. Now, I had mentioned that we had no information on the statistical background for this concrete. When we have no information for the statistical background on the concrete, we use table 5.3.2.2. This is the table to use if you have no production results. When we say no production results, what's an example where you may have production results? Or you may be able to use a different table? Right, if you've got more than 15 samples of a similar concrete that's being made out of a production facility, you can take advantage of knowing something about your quality control procedures and your consistency procedures. And what they're going to enable you to do is they're going to enable you to design the concrete closer to the specified strength. Right, so you may remember that essentially what we're looking for, you'll remember our bell-shaped curve, and I hope I didn't draw this in the wrong spot, but you'll remember that we have a specified compressive strength. We are going to target a higher required compressive strength that's going to be some value to account for statistics. The basic idea here is if you have a lot of historical data, you can make this difference much smaller if you've got good quality control. This table that I've shown here is going to be the most conservative, which means it's going to have the most over-design associated with it. So for our particular example, which I obviously did draw in the wrong spot, we are targeting 3,500 psi concrete. So that is our specified compressive strength. 3,500, the last I checked, is going to be somewhere between 3,000 and 5,000. So we're going to be on the second row. So we would take our specified compressive strength, we would add 1,200 psi to it, and we would be targeting 4,700 psi for our design strength, our required average compressive strength of our cylinders. Now we can come in and we can select the water to cement ratio using a table like this one. I will point out that you will notice that 4,700 is somewhere, not somewhere, it's 7/10 of the way between 4,000 and 5,000. So we're going to be somewhere between a 0.4 and a 0.48 water to cement ratio. Because 4,700 is closer to 5,000 than it is to 4,000, we're going to be closer to 0.4 than we are to 0.48. Linear interpolation can actually tell us what the exact value of this is. So we can determine the water to cement that we're shooting for by taking our 0.48 water to cement ratio, the difference between the two, and simply doing a linear interpolation between those 2 points, and we would come up with a 0.424 water to cement ratio for our particular design. Given this 0.42 water to cement ratio, we can now start to compute the cement content. You'll remember we had 270 pounds per cubic yard for our water by weight. We've got a 0.42 water to cement ratio. We know the water by weight or by mass. What we need to determine is the cement. We can simply rearrange this equation and calculate out that we would need 643 pounds per cubic yard of cement. Now, at this point, you would want to double check to make sure that you don't have some sort of a limitation on the minimum cement content for your particular region. Here is where you would go to a code and you would typically see that they would have a requirement of something like 564 pounds of cement per cubic yard. That happens to be a fairly typical standard in the Midwest. 564 pounds may sound very odd. Does anyone understand where 564 may come from? Why would we have such an odd number?
Bags of cement.
Right, it's based on the old bags of cement, and everybody knows that a bag of cement weighs in the lower 90s, 92, 94 pounds, somewhere in that range. Right, back when cement all weighed the same. Now around the world they're changing the weights because apparently it's illegal in some parts of the world to lift 92 or 94 pounds. If you multiply that out times 6, what you'll end up with is 564 pounds, and that's where that very odd number comes from. So if you hear people talking about 5-bag, 6-bag, 7-bag mixes, you can basically take that number, multiply it by your 94, 92 value, 94 value, and then that's where that number's coming from. Now, determining the air content, here is where you would go to a manufacturer's data sheet. So, for example, if you're using a particular air entrainer, you can go onto any of the manufacturer's websites. You can download some information on that, and they will tell you recommended dosage rates. We can assume for the air entrainer that we're using, it's 0.9 fluid ounces per 100 pounds of cement. This is a fairly typical nomenclature that's used to specify the amount of admixture that we would use. One of the things that I will point out is a lot of times you'll see this pounds per 100 pounds of cement listed as something like CWT. You will want to make sure that whenever you're doing fluid ounces, they're typically done on 100 pounds of cement. So here we've got 643 pounds of cement times 0.9 fluid ounces per 100 pounds is going to give us something like 5.8 fluid ounces. That would be our initial design for this particular mixture. Mike? In reality, what you should be doing is determining the amount of water that's in the admixture and subtracting that out of your mix water. But a lot of times that's a relatively small number. When we start to get into real high-performance mixtures with a lot of different admixtures where you can have a lot of water, you do want to make those corrections. Okay. We're not going to do that here because it's a relatively small number. I mean, you're looking for each yard. We're talking about 6 fluid ounces, which is pretty small. Okay. Step 7, estimating the coarse aggregate content. Again, remember we wanted to know the finest modulus of our sand. For our particular problem, it's 2.8. 3/4 inch aggregate. We get this number 0.62. This 0.62 number represents what physically?
Volume occupied by dry rotted.
It's the volume of the system that's occupied by the dry rotted aggregates. So we would have 0.62 cubic yards occupied by our coarse aggregate. This is our dry rotted portion. And we could go through now and we could figure out that if each yard is 27 cubic feet times 0.62, we would have 16.74 cubic foot of aggregate in each cubic yard. We would multiply that by our dry rotted SSD weight, and we would come up with 1674 as our overall weight for our coarse aggregate. Now the next thing that we need to do from here on out is really sort of accounting. We want to do accounting to determine our amount of fine aggregate, and we want to do accounting to determine the amount of any sort of moisture adjustment that we would need to do in our overall system. The specific gravities of our materials are going to be given. We know that water has a specific gravity of 1 because specific gravity represents what?
Density of material to density of water.
Right, it's the ratio of the density of any material over the density of water. So water over water should be unity, should be a value of 1. Cement is going to be 3.15, somewhere between 3.1 and 3.15 times as dense as water. Air we're not going to worry about for right now. Our coarse aggregate was mentioned to be 2.68. Our fine aggregate was 2.64. If we multiply all these by our density of water, and I will erase the little divided by sign there, and that should have been a caret to be pounds per cubic foot. What we would end up with is we would have 62.4 being our water. Our cement would be 3.14 times 62.4 is 196.6. Coarse aggregates 167.2. Fine aggregates 164.7. We have the weight from going through our particular examples. 270 pounds was our weight of water. 643 is what we got for our cement. 1674 is what we just calculated out for our coarse aggregate. And if we divide our weights by our densities, that tells us what the overall volume of those materials are. So what we can see is in a cubic yard of concrete, which is going to be 27 cubic foot. So for the full cubic yard of concrete, we would have 27. 1 yard is 27 cubic feet. What we would notice is that 4.33 cubic feet of that is going to be water. 3.27 is going to be cement. 1.89 is going to be air, and we got this by, how did we come up with the 1.89? It's not simply the weight divided by density.
Percentage of.
It's going to be 6% times our 27 feet, and that's going to give us this 1.89 number. 10.1 is the cubic feet associated with our coarse aggregate, and if we add that all up together, we get 19.5 cubic feet. That means that the leftover space is going to be 27 minus 19.5, which tells us that 7.5, which I've got in our middle spot here, is going to be the missing volume of our aggregate. So in order to calculate how much that is, we've got 7.5 cubic feet times 2.64, which is our specific gravity, times the density of water, gives us 1,236 pounds of fine aggregate in our mixture. So we now can take this a step forward, and we know our saturated surface dry weights of all of our materials that we had gotten from our previous slide. We've got 270 pounds of water, we've got 643 pounds of cement, we've got 1,674 pounds of our coarse aggregate, and 1,236 pounds of our fine aggregate in our overall system. Now the final step that we need to do is we need to make an adjustment for the moisture content in the aggregates. So what we really want to try to do is we really want to try to figure out our aggregates are going to be somewhere between oven dried, which is sort of one end of the extreme. They're going to have more moisture content than oven dried. Now why do we actually talk about oven dried? What does oven dried help us out with? Right, can you give us the absolute amount of water? And it's very easy to determine. So everybody in the room, presumably, can find the oven-dried state. Take some rocks, throw them in the oven, come back 24 hours, plus or minus 12 hours later. So even if you take a nap and wake up too late, you can come back and find the oven-dried state. But what we really want are our aggregates in this SSD condition. SSD condition is sort of this magical place where we just have enough water inside of the aggregates that it's going to fill the internal pores, but we don't have water clinging to the outside surface of the aggregate. And the reason that this is incredibly important is because it won't release water into the system to make the water to cement ratio go higher, or it won't suck water out of the system to reduce the water to cement ratio and make our concrete's workability go down. So what we want are pores that are just filled with water. The surface is just wiped off with a towel in the case of a coarse aggregate. We've just lost cohesiveness in the case of a fine aggregate. And what you will notice is that our sand had our sand was 0.7. It's in a state where it's 0.7, but 0.5 was our absorption capacity. 6% sand, 6% is where we're at with our, for our coarse aggregate, we are at 0.7% moisture content. 0.5 is our absorption capacity. Let's try this one more time. Let's look at our blue diagram being the absorption capacity. 0.7 is the absorption capacity of our sand. 0.5 is the absorption capacity of our coarse aggregate, so that we now have that. Our moisture content is going to be 6% in the case of sand, 2% in the case of coarse aggregate. What you will notice in both cases, we are greater than their absorption capacity, which means for the coarse aggregate, we may be somewhere out here. For the fine aggregate or the sand, we're somewhere about 3 computer screens over in terms of moisture content if we looked at this to scale. So for our coarse aggregate, we're at 2%. We should be at 0.5% in the SSD case. For our sand, we're somewhere out here at 6%, way off the screen, and we should be down here at about 0.7. So what we need to do is we need to make an adjustment for that. So we know our moisture contents. We know our absorption capacities. We can take the difference, and this is the amount of water that we would need to adjust out of our mixture. So what we can actually do now is we can go through and we can make this adjustment. We can say that a portion of this weight, if we were to just weigh out our actual materials out of the stockpile, they would contain excess water and not enough aggregate. So what we need to do is we need to beef up the amount of that aggregate that we're actually using in the system, because there's going to be a portion of that that's just plain water that's coming along for the ride. So we're going to take this small percentage right here, 1.5%, times 1674, and that's going to give us our 25 pounds extra that we're going to add to our mixture. We're going to do exactly the same thing for our fine aggregate, 5.3% times our 1236. That's going to be our 65 pounds. So what we're actually doing is we're adding in an extra 25 pounds of coarse aggregate because it's going to contain excess water with it. We're going to add in an extra 65 pounds of fine aggregate because it's going to contain 65 pounds of excess water. If we're adding in extra aggregate because it's containing extra water, that means we need to reduce the amount of water that we're putting into the mix. So we're going to reduce the mixed water by simply the sum of the coarse aggregate and the fine aggregate and the water that's coming along with them. So if we go through, we can actually do the calculation on that. Instead of putting in 270 pounds of water, we'd put in 180 pounds because we're getting additional water coming from our sand and coarse aggregate. We'd have 643 in terms of cement, 1,700 in terms of our coarse aggregate, and 1,300 in terms of our fine aggregate. Now, what does this mean? If we didn't do this correction, and this is a pretty severe case here, if we didn't do this correction and we just added the aggregates using their stockpile weights and not making these corrections, in the SSD condition, we would have had our water to cement ratio of 0.42, which is what we designed on. If we didn't make that correction, we would have actually had less aggregate than we expected and a portion of extra water. We would have had less fine aggregate than we expected and a portion of that which would have been extra water. And we would have ended up with a water to cement ratio that was much higher. We would have had quite a bit of excess water. So instead of having a concrete that may have had, the 5,000 psi or 4,700 psi that we would have been targeting, where we were out in this range, we would have had something that was about 30% lower if we didn't do our correction. Now, that's a pretty extreme case, but that's to give you a little bit of an idea why this is important.
Now, does that affect your slump at all?
Oh,
Assuming that you have water in your aggregate.
That'll affect your slump in a very dramatic way. If you have excess water with your aggregates and it's getting you a lot more water to cement ratio, it's going to be a much more fluid mix. And this is really why the slump test came into being when they were doing these lightweight aggregate ships. They were wanting to control the moisture in the lightweight aggregate. I mean, in these cases, we're talking about, those numbers were in the order of, I think it was 0.7% and 0.5%. Is that what the absorption capacities were? when we talk about a lightweight aggregate, the lightweight aggregates you're using, Ryan, are about 10.5%. So those are huge numbers that we would need to be adjusting for if we don't get it right. So a lot of times they're actually going to be pre-sprinkling the lightweight aggregate so that it's not absorbing water out of the system or it's not giving back a lot of water to the system. But you would see huge differences in your strength and huge differences in your slump. And one of the biggest things is if you go to a place that's having problems with quality control, one of the things that they're usually doing a real poor job on is controlling the moisture in their aggregates. And they're just getting a lot of excess water in the system. So they'll have their strengths bouncing around, the workability of the concrete's bouncing around out in the field. And typically the best way to do that is come in and do a little bit of process control on your aggregate.
Now, does the fact that the water might be inside the aggregate affect the slump? Does that make any sense?
Well, we want the aggregate, we want the water inside of the aggregate. We actually, the SSD condition that we're coming up with is based on the assumption that all the pores are filled. Now, that's a little bit of an assumption because one of the things, and I know that it went by pretty quickly, but I showed a graph of the logarithm of the water uptake in an aggregate as a function of the log of time, and we noticed that it was linear with the square root of time. So the aggregates will suck up water very quickly, but they'll suck up water for days and days and days. So we assume that they're in a saturated surface dry condition, where in reality, if you throw in an oven dried aggregate, it won't quite get to saturated surface dry by the time the concrete sets. But that's an assumption that we make here. Now, you could do other calculations if you wanted to get it even more precise, but that's sort of the accepted calculation. Okay, that sort of answer the question? Mike?
Since our original weights before we did the adjustment were for a specific volume, when we adjust the aggregates in the water, what happens to that volume that we specifically designed for? Like 1 cubic foot of concrete, we get these weights and then we adjust. Is it still going to be?
What we're just doing is we're just sort of re-partitioning where the water's coming from. The volume should be the same. One of the ways that we're going to actually look to make sure that our material is as designed is we're going to do things like a yield test, where we're actually going to weigh a cubic foot of the concrete when it comes out. And we're going to make sure it weighs what it's supposed to. And if it doesn't weigh what it's supposed to, that means that there's some adjustment that's been taking place, throughout the process. As I mentioned, I believe it was about 2 classes ago where you could use unit weight to track air. That's one of the things that's most commonly done because you'll notice in these calcs we didn't say anything about the air because obviously air is going to be really, really light. All right, so we're going to assume that it's going to be effectively 0. But if we start not getting 6% air and we get 3% air, this won't actually yield a cubic yard of concrete. It's going to yield a smaller amount. So if you fill up a bucket, it's going to weigh more for that concrete. Okay? Other questions? All right, second look at some of the aggregate calcs. As we mentioned, we are frequently very interested in the surface area of the aggregate because it's going to dictate our amount of paste. As I mentioned before, as we go to smaller aggregates, the paste volume increases, and this is because we have more aggregates to coat. Aggregates that are half the size, which is typically the next size smaller, requires twice as much paste because we've got twice as much surface area in the overall system. We did the gradations. I'm not going to spend time talking about that. But one of the things I did want to spend a little bit of time on was this idea of the fineness modulus. Wanted to just hit this again in case you actually needed to calculate this. The fineness modulus is simply a way here of sort of quantifying or accounting for the surface area associated with the sand. So when we saw all of these different values in this table, they're a way that's sort of accounting for the amount of surface area, the fineness of the sand are in each of these columns. So what you would actually be doing, there are two calculations that you want to typically be doing. Most of the time these calculations are very sensitive on the fine aggregate. They're much more sensitive on the fine aggregate than they are going to be on the coarse aggregate. You want to be running your daily moisture tests. In theory, you want to be doing this on both the coarse aggregate and the fine aggregate to be making your daily batch adjustments to the water. But you also want to be running your gradations to verify that your aggregate not only meets ASTM C33, which is sort of the broadest standard that's out there, but make sure that you're not changing your fineness modulus each day. Because if you're changing your fineness modulus, obviously your paste demand is going to be very different. The amount that you need to coat those aggregates is going to be very different. Let's assume, to determine the fineness modulus, let's assume we've got a 500-gram sample of sand. It was found to have the following materials. The weights are retained on each sieve. Calculate the fineness modulus of sand. Now, one of the things that I will point out is fineness modulus is going to be determined by calculating the cumulative weight that's retained on each of these sieves, the number 4, the number 8, 16, 30, 50, and 100. If you have other sieves, you are not going to consider them. There are 6 sieves that we are interested in considering, and these are them for sand. Right? These are the ones that you want to consider. This weight over here is the weight that's retained on each one of these sieves. This is what you would be weighing out on your particular scale. You would take each one of those numbers and you would determine the percentage that's retained on each of the sieves. That is simply going to be the weight of the number 4 aggregate divided by the total weight. So for the number 4 aggregate, we had 15 grams. The total weight of our sample was 500 grams. We would end up with 3% by weight retained on that sieve. We would do that for all of the other sieves, and one of the beautiful things is this is one of those types of calculations when you do it every day that can be automated quite nicely so that you don't have to run through it. 60 over 500 would give you 12%, 100 over 500, 20%, 21%, 26%, and 18%. Now, the cumulative percent retained is simply going to be the summation of these as we work our way down. We work our way down through the problem, and we would end up with 3%, 15%, 30% all being retained. We would sum up those cumulative values, divide by 100, and that is going to be our fineness modulus of our overall system. One of the things that is not included in this is the pan measurement. So a lot of times you will see that these numbers don't total up to exactly be this number that's right here, and that's because some of that material is going to go through and it's going to be finer than the number 100, and that's one of the things that you should notice from the spreadsheet that you got. So one of the next questions is, okay, we've now gone through our whole process. We then go out and we do a trial batch, and the purpose of the trial batch is to do what? Check to make sure everything goes as planned. So we attempted to get a 3-inch slump. Did we get a 3-inch slump? One of the next big questions is, I got a 6-inch slump. I wanted to get a 3-inch slump. What do I do now? All is wrong with the world. What's the next step in the whole process? So there are a few tables that you can actually look at. These tables, I think, give us a little bit of information on how to make some fairly quick and rapid adjustments. The first table that I'm showing you, the first graph that I'm showing you, is the air adjustment graph. Along the x-axis, you've got the amount of air that you wanted in your particular mix. Along the y-axis, you've got the actual amount that you've measured. So for example, if you wanted to target 6%, like we were trying to do in our problem, but you measured 1% from the actual test, you would be somewhere down in this region down here. Okay. Now, an example of how this would be done, if everything was exactly like you had planned, you went, you did your design, you got exactly what you wanted in your trial batch, you would desire 6.5% by volume, you'd follow this green line up. You would measure 6.5%, you would follow this green line over, and what you would find out is that you would be right on this line that has a 1 written right after it. All right? That 1 is essentially a multiplier. That is the adjustment that you would make to the amount of air entrainer that you're using in the system. 1 times whatever air entrainer you're using in your system gives you back the amount that you used originally, which makes sense because you got exactly what you wanted. So in the case where everything went exactly as planned, you will end up along this line that has a value of 1. Most of you would not go to this table if you got exactly what you wanted to make an adjustment. At least I would hope. When you would go to this graph or this table, you would be looking to say, I wanted 6% air, which is shown here by this red line. I actually got 3% air. What do I need to do to the amount of air entrainer that I'm using in the system to make this work out? You'll notice that they follow along a line that I'm trying my best to trace out, and it's not that I've been drinking during the day. I don't know, the mouse is going a little wild on me here, but this used to be a straight line, and you'll notice that this line has a number 4 on it. That is the amount that you would multiply your admixture dosage by to try to correct for the air that's inside of the system. Okay? So this is a simple multiplier that gives you a good way to sort of multiply your air and training admixture and helps you get into the system fairly quickly. If you found yourself halfway between the 0.35 and the 0.5, you could wing it, you could interpolate, you could make an adjustment or a guess and assume that you would multiply by something like 0.42. So if you're up in this region, you're above the 1 value, that means you need to back off the air and trainer. If you're down in this region, that means you need to add the air and trainer to the system. Next question is related to slump. What happens if I didn't get the slump that I wanted in my particular concrete? What do I need to do, the amount of water that's inside of the system? Again, it's set up the exact same type of way you saw in the previous graph. Here you've got the desired slump being along the bottom axis, the measured slump being along the y-axis. If everything went exactly as planned, you wanted a 4-inch slump, you got a 4-inch slump, you would be right here where the two green lines intersect. And you would notice that on this axis, there's a value that is 0 kilograms per cubic meter and 0 pounds per cubic yard. That's the amount of water that you would add or subtract from the system. If you didn't get exactly what you wanted, let's say you wanted a slump of 125 millimeters or 5 inches, you got 3 inches, you would follow along this line that tells you to add 10 kilograms per cubic meter or 17 pounds per cubic yard of water to your overall mixture. Now, you can either add that water to your overall mixture, you can make that adjustment to your water content, or you could figure out what the equivalent would be for something like a water reducer. You'll remember your water reducers, we gave you some rough ideas. They were 5%, 8%, 12% of the overall water content. You can make an adjustment here to figure out how much that would be for the particular admixture that you're using. Questions on that? Mike?
Is it common practice for them to just add water in the field? Like, are these decisions made in the field, or are they made at
No, these would be made in the design process.
Okay.
All right, and next week we will use my favorite slide where I have used a standard 96-point font to tell us that indiscriminate additions of water should not be tolerated in the field. We do not want to be adding water in the field because we've redesigned the entire mix. This you're going to do at the step where you've done your mix design. You've gone to do your trial batch. You don't get the numbers you wanted to get, or you don't get the numbers you expected to get. How would you adjust it to redesign the mix, to redo a trial batch to make sure you're going to get the concrete that you're after? Okay. Similarly, we will see the exact same type of graph for making an adjustment of strength. X-axis, again, is our required strength, or this is the strength we're designing for. The measured strength is what we're seeing along our y-axis. If everything's planned, again, you're along the green line. You don't do anything at all to the system. What you would notice here is if you're not where you want to be, you might have been designing for 40 MPa, you got 30 MPa. You'll notice that you fall along a line that has a minus 0.1. This is the adjustment that you would make to the water to cement ratio. So you would drop the water to cement ratio by a value of 0.1, which is a fairly severe change to the water to cement ratio of the system. All right, but that will help you to figure out how to get your strength back in line with what it should be.
Wouldn't, if you were to do that, wouldn't they just send you back in circles with the whole reducing the water? Because say you go to adjust for this strength, wouldn't that throw off the other chart that had to do with reducing or changing the water or adjusting the water?
Yeah, usually what's going to happen here is you're going to start to go back, and what you're really going to be doing is changing the volume of the aggregates probably in that case. So you're going to have as much water. You're going to have a higher water to cement ratio. So you're going to need more cement in the system, or a lower water to cement ratio. You're going to take cement out of the system. You're going to be adjusting your volumes there. But yeah, I'm going to say if you're off this much, then you're pretty much going back to the drawing board and starting over. Okay. We could go through, we could do an example where there's going to be different types of cements and different types of admixtures being used. It's becoming increasingly common not to see just a single ordinary Portland cement being used in the mixture, but seeing something else used in the mixture to try to take advantage of some of the other binders that are out there. We will go through this fairly quickly. Give you some broad ideas on exactly what we're trying to look at. Again, your cement is going to be just an ordinary Portland cement. Specific gravity here, to throw in a little bit of spice of life, is not 3.15, it's 3.14. Way that we're going wild on a Friday afternoon here. Fly ash is going to be a type F fly ash, which will typically come in when we start to talk about the volume of the material that we're actually looking at. Specific gravity is going to be 2.6. Slag is going to have a specific gravity of 2.9 and an SAI of 120. And SAI sounds like something we're using to rank college basketball or football teams. But an SAI is what?
Relates how quickly it gains strength over cement.
Okay. Our slag activity index, it's going to basically be relating how fast the slag is developing strength compared to the comparison cement. Coarse aggregate, 3/4 inch aggregate, 2.68, going to look exactly like what we saw in our previous example. The only difference is this is a more educated material because it's now in the metric system. Our fine aggregate is going to have a finest modulus of 2.8. Same as we saw in the previous case. Here we're going to want to use air, which is going to be 0.5 grams per kilogram of cement. Our water reducer, 3 grams per kilogram, and a high-range water reducer that would be used here being our 30 grams per kilogram. So I believe we talked a little bit a few lectures ago about using a water reducer and a high-range water reducer, or using multiple types of admixtures together. Now that we're getting much more familiar with this whole process, we could go through some of the steps a little bit more quickly. Step 2, we would assume that we would have a 50 millimeter slump before plasticizer. When the plasticizer is added, we may expect to get something like a 5-inch slump maximum. One of the things that you typically want to do if you're using a high-range water reducer or water-reducing admixture, you want to watch out for segregation. If you get a lot of superplasticizer into the system, what you're going to do is drive down the yield strength of your paste. When you drive down the yield strength of your paste, it's typically going to be easier for some of the aggregates to fall out of suspension, and you're going to get to a point where you're segregating a lot of those aggregates. Step 3, maximum size of your aggregate. It was 19 millimeters. You can check the size and spacing on your elements, check your cover, but the maximum size of the aggregate was given. Step 4 is to estimate your water content. Again, we're looking at something without the water reducer that would have a slump of about 50 millimeters. We could reduce this by about 10 to 15% due to the combination of our water reducer and high-range water reducer, so we might take this down to 143 kilograms. Severe exposure, we'd have 6% air. You could select your water to cement ratio. Again, here what you're going to do, let's assume that you've got a little bit of previous knowledge. You could go in, you could enter those other tables that allow you the fact that you're targeting 40 MPa. You get 2 MPa standard deviation. You're going to take the lower of the two values, 40 plus 1.34 times the standard deviation, or 0.9 times 40 plus 2.33 times 2. Take the higher of those two values, which is 42.7 MPa, and then you could go out and check your water to cement ratio. Now here, what I've also thrown in is that you may make adjustments depending upon some of the old data that you've got using similar aggregates or using similar mixtures. In your old lab, you found out that 0.35 water to cement ratio yields a 43 MPa concrete. You might use 0.35 here because you're after a 43 megapascal concrete. Compute your cement content. We've been through this a few times now. This is going to be your total cementitious content. 143 divided by our 0.35 water to cement ratio gives us 409 kilograms, and that's our cement by total weight in the overall system. Again, you want to check on this limit, and that's going to make a little bit more sense in a few seconds. Now, I mentioned that you may want to use some other binders in the system. Here I'm going to assume, based on local history and what's common, we've got a type F fly ash, which is usually used in about the 10 to 20% range. So we will use 15% type F fly ash. We will make a shot at using 30% slag. I will come back in a second to tell you some of the other things that you should be considering when you start looking at your fly ash concentrations. 403 kilograms of cementitious, 15% fly ash times 403 tells us 61 kilograms is going to be our fly ash. 30% times 403 is 123 kilograms. The remaining part is 225 kilograms. Check the total percentage of the supplemental materials that you're using. They are less than 50%. That is one of the important checks that you typically want to do, because there is a maximum that you can have for materials that are going to use de-icers. Fly ash, you need to stay below 25% in a system that's going to be exposed to deicers. Slag, you need to be below 50%. Silica fume, you want to be at 10% or less. The total of everything except slag should be 35%. The total of everything, including slag, should be less than 50%. Now, why would slag be excluded from our fourth line down?
So similar to cement?
All right, because it's the difference between hydraulic and pozzolanic. Exactly. If it's fly ash and our silica fume are going to be much more pozzolanic, so they are not going to react simply on their own with water. They need to have the calcium hydroxide in the system. And if you get above some of those values, you get above about a third of the system, you're just going to simply run out of calcium hydroxide in the system. So we typically want to limit those. We can go a little bit higher if we're adding slag in because it has its own hydraulic properties. Again, we can go down the list, use our finest modulus, estimate our bulk volumes, calculate out the volume of cement, 992 kilograms. We can make our adjustments for our admixtures. Again, we've got our air, our water reducer, our high range. We can make all of these adjustments. And then we would include the water of each of these in the following calculations like we had talked about a little bit earlier, where we would figure out the water that's in each one of these admixtures, and we'd go ahead and we'd use this. Okay. Much like before, we would simply figure out the volume that's missing. The volume that's missing is going to be our fine aggregate. Now, one of the things that I will point out here is I didn't do a lot of any sort of corrections based on the fact that fly ash may be less or more effective than a cement. I just went off of the percentages. The only other thing that I threw into this table that we hadn't seen in the previous table was I added in the specific gravities of the fly ash and slag, and we carried those through in the terms of our calculations of our volumes. You would do the exact same type of correction for the moisture in the aggregates just like you did before. The same type of correction would be done to make sure if your aggregates are too dry, you're adding in a little bit less aggregate and adding some more water into the system. If your aggregates are too wet, you're adding more aggregate and taking away some of the water out of the system, making those adjustments. Questions or concerns at this point? Okay, there is another example that you can go through. I mentioned that I would put an example up. I simply put that example up here in Word. Well, I put the example up in PowerPoint. I'll post a worksheet that you can actually work through in Word so you can see where some of these values are coming from, where the selections are made. One of the questions, you're going to get questions like this to be doing on the homework. One of the questions that I'm going to be asked, I am sure by someone, is will I ask you to do a complete mixture design on the exam? You should be able to do each part of the mixture design on the exam, so I may give you a mixture design that's started, and you may need to make the next calculation. I may give you aggregates. You may need to do the adjustment, but I can promise you that I am not going to give you a start to finish do this particular mixture proportion, because there are about 1,000 different ways that people can go in a different direction, which means I would be grading for the rest of my life, and also people end up getting into some weird calculations when they start going in their own direction and voyaging off in that way. All right. At this point, we are going to take a voyage sort of sideways from what we've been talking about up to this part of the class. The first third of the class really deals with constituent materials, and I think we've talked about just about everything that you could jam into concrete other than fibers. We've talked about the water, we've talked about the rocks, we've talked about the cement, we've talked a little bit about the structure of the system, we've talked about the supplementary materials. For the next, what I would say the next third, although it's a shortened third of the system of the semester, we are going to talk about some practical field aspects. We're going to talk about batching of the concrete. We're going to talk about curing of the concrete. We're going to talk about field placement of the concrete. And the last third, which again is going to be slightly bigger than a third, what we will be talking about are the mechanical and durability properties of the concrete. So you should expect on Monday we are going to take a slight voyage from the types of lectures that we've been talking about. We're going to voyage off into batching of concrete. We're going to start to talk about what are some of the important things at a plant. We're going to start to talk about some of the important aspects of how batching is done, some of the important considerations, and we'll take things from there. Questions? The final thing that I will mention in my last 18 seconds before I release you on a Friday afternoon, the last thing that I will mention is there will be a new homework that will be going up, but we will let that go up on Monday. So on Monday, look for new homework that will finish up our stuff on constituent materials. Have a good weekend.